Okay. Hello. Welcome to lecture 2. Ooh. So here we are. I kind of lost a little bit my trust into the technical university when we lost Wales last week. So, but I gained my trust again, because what I did is, first thing is we have this magical support, which is called Pro Lehre, where you can just bug them of anything. So I wrote them an email of okay, so there should be another way of how I can do this. And then I was like, because I felt, it's probably impossible that they can fix the bias, right? I mean, typically not in a few days. But then in the evening on Tuesday, I was like, no, you should write to the IT people. Maybe they can fix it, right? So I wrote an email at 9:11 Tuesday evening to the IT people in the physics department. I had a reply at 9:18. I'm going to take care of it. Same evening. So I'm very impressed. And so what they did for now is that they patched a new enhancer next door, and so hopefully that should get us through this class. And if it doesn't, I do have a LAN, and I will just disconnect the LAN of this thingy here. And if all of that doesn't work, then next week I'm going to try all the things that I got told by Pro Lehre. So, we're actually organized and it actually does work. And so now it works here too. Any thoughts, questions? So then we can just dig in into lecture 2. And so so today what we're going to do is we're going to look at the correlation function again. Correlations, and this will be with fluctuation and dissipation. And then we'll go into universality, and maybe in the end start talking about field theories. Okay, so so the last thing we started on Tuesday was to look into correlation functions. And so let me just first write down the definition one more time, and then we're going to look at an image, because this explains it much more than anything else. So it's defined as the spin versus the average in its correlation in space if I consider a spin at position I versus a spin position J. And so this is a map of spins actually at a critical temperature for a 2D Ising model, ARCA ferromagnet. And so what this correlation function is actually measuring here is what are the fluctuations the spins have relative to the mean value. So if you're at 0 temperature, and you have an applied field, all spins should be pointing in one direction. So there aren't any fluctuations, right? And so, but what happens here is that as you increase the temperature, there are fluctuations, so you can actually measure fluctuations. And at the critical temperature, these fluctuations become sort of self-similar. And this is what you're supposed to see here, in the sense that there are correlations of these spins sort of on short distances. Like, I have the this and this patch, I find statistically correlation on this size, but I even find them on these big size and also all intermediate sizes, if I just focus on the black spins. And the same is true, obviously, for the white spins, so the ones pointing up and pointing down. So the hallmark is that at the phase transition, I get these long-range correlations. Yes, there was a question.
Yeah, with your description of self-similar, does it mean that it doesn't matter how far you zoom in or out, it looks the same?
Yes. Okay. And so that's how you see that the fluctuations are self-similar, right? Because the if there were long-range correlations at t equal tc, if we were at t bigger tc, say, correlations would decay exponentially. And we're going to see this mathematically soon, but just to sort of, for you to have an intuition. So what I expect for a non-critical system is that if I have spins and the spins are pointing all up, then they if I'm above the critical temperature, there is a spin that's pointing up, so it creates a little bit of a local field. So it's very likely that a spin just next to it will also point up. And so there is a little bit of a correlation of spins being in a similar configuration for like spins that are close to each other, but eventually due to the fluctuation, this will be washed out and there will be an exponential decay of my next nearest neighbor being in a different state than I am. So if I'm pointing up, this one will point up. So this is very, very likely to happen, right? And what happens at the critical temperature is that these correlations become, what I said, self-similar, in a sense that if we take this image and we were to zoom in, we would still see that, we have these tiny patches where there is correlations, and then on all different scales, I would see correlations of having small patches and big patches similarly distributed within the setting. And that's the reason why we care so much about being able to calculate correlation functions. So what we're actually doing, these almost like the first 3 classes, is building up vocabulary in a sense. So I don't expect you to understand all these individual all these concepts. It's just advertising. Okay, these are these concepts that we're going to talk about, and this is why we care about them. And then starting from next Friday, we're really going to jump in and like bit by bit derive how all of this emerges. But this is take it as like vocabulary training so that we're all prepared. So that's why we care about these correlation functions. And so what we can do is that these correlation functions, we can actually relate them to the magnetization, and it turns out that we can even relate the these fluctuations to one of our response functions. Remember last week we did this recap of statistical physics, where we started with the partition function, how to calculate the free energy, and then from the free energy we did the first order derivatives, which, for example, for the magnetization would be derivative of the free energy, and then we also did these second order derivatives, where we would, for example, find susceptibility. And so these second order derivatives, this is what we call response functions. And as it turns out, these are actually connected to these fluctuations. So the fluctuations that I have in a system tell me something about the, a seemingly at first sight unrelated property, namely the response function, which I would normally get from the free energy. And so why this is the case, this is what I want to show you, and it's a little bit of a derivation. That's why I stopped close on this point. on Tuesday. Okay, so what we're aiming for is relation between fluctuations so we know that the magnetization of a whole system we can write as the sum over all individual spins. So I'm just summing up all. So if like half of them are pointing up, half of them are pointing down, I have a zero total magnetization. If all of them are pointing up, I have the maximal magnetization. Why do we need this definition? Well, because we defined the correlation function as the fluctuations in spins. And now we want to rewrite it as a function of the magnetization. And remember, the magnetization, that was already the first order derivative of the free energy. And so rewriting this in terms of the first order derivative, you can see how we might get to a relation of these fluctuations to the second order derivatives, so the response functions. So if I spell it out and look at this quantity, then this is actually, and if I now write the magnetization in terms of spins, then what this actually is nothing else than SI minus the average SIs times SJ minus the averages. Note this is squared here. And this, okay, this is what we know, right? This is this product here we can identify as the correlation function, and what we're left with is that there's also sums of it. So it's the sum over the correlation function that that actually shows up here. So that's one thing that we know. And then another thing that we know is that actually the mean magnetization we also know as being the derivative of the free energy, or if I write it in terms of the partition function, I can write this as d ln z d beta h. Now, for like a ferromagnet, as shown in the picture above, we know that the partition function is the sum over all states, which I can, as we're going to see, write as the trace of all states in the system. So this is the Hamiltonian of the partition function, where this is the internal energy of the magnet. And here H is the applied field. And so this is the applied field and the resulting magnetization. And so if we, for now, just take this definition of the partition function for the system as a given, we'll introduce it next week. We can see that then this magnetization here, which is the derivative of this partition function with respect to beta H, actually, gives me really this the average magnetization. And so I can also write this in terms of 1 over Z which is just the definition of the average magnetization. So that was the magnetization. And then we had that the susceptibility is the second order derivative. So this is now taking dm dh. And so if I do this now, being aware of this relation with the partition function, I arrive at So I have one contribution from the m coming down one more time, which gives me an m squared. And I have another contribution from taking the derivative of this factor, which gives me and so that in the end actually means what we're looking at here is in this case, that's the sorry, this is where it isn't. This is the square mean value here, and that's the mean value of the square of the magnetization. Yes.
I have a question regarding the first. You're splitting up on the correlation function, the average of the magnetization. This splitting up with I and J is not the condition. It is only allowed if your variables are identically and independently distributed.
The splitting up in SI and SJ. Yeah. So we did state this last week, right? That we're for the magnets, we're always in the Boltzmann condition where we have, yeah.
From last week. Okay.
Yeah, we have, or Tuesday, right? Yeah. So it feels like a week. I can see that. Especially the first week, right? Yeah, it's like we're always in a classical example where we have distinguishable particles. Yes, because the spins are localized in space, and that's how.
How is it fulfill the condition for independent? So independent distribution. They are not really independent if they can influence each other.
What do you mean with independent? This is just like a statistical measure. Like there's nothing, I don't say anything yet about how they are interacting, because like this you could write down for any gas whatsoever. Where the physics comes in is when I define the partition function. Because the partition function here in the energy, this is where I define how elements are interacting with each other. And I agree, I haven't defined this partition function, which is like, again, I'll show you the how for a generic given partition function, we can arrive at the susceptibility being related to the fluctuations, which is what I want you to learn. And then we'll delve into how different partition functions will look like that we will be staring at a lot. I believe next Friday or next Monday. I have no idea. Well, we'll see. Yeah. Okay. So looking at different models, we're going to introduce all the models in detail. So, but if you just take this, what is it? The partition function as a given, we can see that, if you just want to calculate the magnetization, it's just a matter of the average magnetization is just a matter of taking derivatives of the partition function. And so if you do it twice, we get two terms. That's actually it. And so the first term, and I'm spelling out the better, is the square of the magnetization, and the second term is the average magnetization squared. And that now allows me to, hey, all of a sudden relate, let me just switch colors, the susceptibility here to these fluctuations, which are then, as we see up here, related to the correlation function. So in short, we have that KBT is equal to the sum over the correlations. And so what can we actually say? The other statements that we can say to just gain an intuition about these correlations. So what the sum actually means, and now we have to use, sorry, let me quickly in this. So for translationally, invariant system, we'll have a look at these the sum of these correlations. So what a sum means is now that I'm looking at all the correlations in space. So it's essentially, I can also, for a translation invariant system, I can look at the correlation of every point. So this is a double sum, but I can also look at like, what's the correlation of position I with all the rest. And this should be for translation in invariant system be exactly the same as looking at I plus 5, right? Because it doesn't matter if I'm where I am. So this is nothing else than n times just summing over I of, say, sigma I of a position, whatever, 5 or 0 in this case. So what we see when we do this step is that what this actually means is like taking a volume integral, right? We're just integrating over the volume of states and the correlation of these states in a translation invariant system. So if we take the limit of n being large, and we see that this sum actually means that we're summing over the correlation functions, which now depends on this continuous variable r. And since we're summing over all the states, it's a volume integral. And so for a volume integral, I have an integration factor popping up, which is d to d minus 1 dr, where d is now the dimension of our system. So for d equal 1, we wouldn't have the integration constant. For a two-dimensional system, it would be r dr. That's the volume integral, and so on. It's kind of unusual, right, that we would write this down with a dimension. So why we are doing this? So it turns out that if or not we are having a phase transition really strongly depends on the dimension of the system. So a ferromagnet in 1D just being a line behaves very different than having a ferromagnet in 2D or having a ferromagnet in 3D. And so that's why this D will actually follow us. And we'll see that the dimensionality of systems is something that's crucial in determining their behavior, whereas lots of other macroscopic quantities of a system do not matter. And so that's why this sort of generic notation taking along the D comes in. So if I take this together, what we just wrote is, again, that this stability is then related to n over kbt of the correlation functions r to the minus mod d minus dr. So, and why don't we now learn something about the behavior of the correlation functions? Because the magic that we did is we now are relating the susceptibility to the correlation function. And we actually know what the susceptibility is doing at critical temperature, right? That was this second order derivative that was diverging, right? And we were so obsessed about divergence because the divergence is easy to track because the dynamics, the behavior of the system is different if I come from the left and to the right, and I know that something has to happen in between. So we know if at criticality x diverges, then this only works if this integral, obviously this integral has to diverge as well. We know that this integral has two components, namely the correlation function and this integration factor. And so it tells us that this correlation must become sufficiently large ranged, has to actually scale with a power law to make this integral infinite. What's the counterexample? If we'd have a correlation function that would exponentially decay, and we'd be integrating an exponentially decaying function with this integration factor, that it wouldn't diverge, right? So it has to be a different functional dependence. And and that's this long range behavior is associated with this depending on R with such that that you have a finite volume that you're integrating and can diverge. Also. Okay. So this now concludes sort of the vocabulary on the observables that we want to classify our system. And so we're going to use them to classify the phase transitions in the system, right? And so let's go ahead and define those. So what are, how do we classify actually phase transitions? So what we look at for phase transitions is a singularity in the free energy. Remember, that was F equal U minus TS for a magnet. Or we would look at the Gibbs free energy, which is F plus PV for fluids. That's the Gibbs free energy in this case. Or if there's a singularity in the free energy, taking the derivatives, we would find a finite discontinuity in the first derivative. Free energy. So that would be, for example, looking in the for the jump and the magnetization for a magnet. Or a jump in the latent heat for fluid. That's the latent heat. Okay, so these are our indicators, and we actually classify a phase transition by where this discontinuity happens, because we distinguish what's so-called first order phase transitions, where interesting. That was me trying to remind me to go to class, but actually being an hour. Yeah, sort of trying to be efficient and actually getting some work done. So okay, so this would be this would be the first order phase transition. Or we can have a second order phase transition. And here what we have is that there's no singularity in the free energy. There's only and first order derivatives are continuous, but then there's a discontinuity in the second order derivatives, and that's how the naming is about. So here now we have a first derivatives continuous. But second derivatives discontinuous. Or even infinite. At phase transition. That would be the divergent susceptibility. Box this again. Okay. So these are the two phase transitions that we care about. And how does this actually look at? Like, let's look at an example. Of a ferromagnet. So how does the free energy landscape look like? So what I'm sketching is free energy. Oops. Nah. So this is T larger than the critical temperature. This is T smaller than the critical temperature. And that's actually at TC. So the key is that here, for the ferromagnet, I have a, as we're going to see, a first order phase transition. And so what we have here is a cusp at T equal TC. If we take the derivatives, like looking at the magnetization, okay. Then as for a negative applied field, magnetization should be negative down here, right? For positive applied field, it should be positive. And now in between is a transition. And this is the case for higher, being higher than the critical temperature, for being lower than the critical temperature. So at low temperature, there's less fluctuations in systems, so the magnetization should be even higher, right? And it actually never really goes to zero, but there's this jump. Remember, we looked at the magnetization as a function of temperature, and this was this that you had to identify the critical temperature, and magnetization was only going down. Sorry, and then the jump starts really at the critical temperature. And so that's the discontinuity that we find in the first order derivative. And so for completeness, also let's look at the second order derivative. That was the first. And here's the second. That is then the susceptibility, which is the M, D, H, T, or D, F squared. Squared. Okay. And then this diverges. So we know that for T equal TC, that we find this divergence. And for this would be for T smaller than TC, and that would be for T bigger than TC. And so here again, the hallmark is divergence.
Question.
Sure.
Is for T equals TC, the jump, is it finite or is it infinitely small? In
the drawing.
Because it seems very unintuitive for like infinitely bigger than TC this to be continuous, but then suddenly if it's TC, then it becomes finite to jump. Like there's no like continuous transition in the discontinuity. If you know what I mean.
I think it's there's a finite jump, but let me quickly check in the book of Yeomans, which I have here. Do you see this? Yeah, perfect. Hopefully, yeah. No, it's finite. This is exactly this drawing. So I can add this here. If this helps, it's figure 2.1. If you don't trust my drawings, which are perfectly fine not to trust, that's okay. Thanks. Yeah, no worries. So that's really this really discontinuous. So you can really spot the phase transition that there's. I think it's much easier to think about it, not in this case in the magnet, but in the fluid, right? So what you do there at the phase transition in the latent, that's the jump in the latent heat, right? So you have to put in this extra energy to break the bonds and make the liquids, the liquid break the bonds and become a vapor. And so this energy is spent into the system inevitably, and therefore you have a jump. Another answer?
Question again regarding the language of criticality and continuity. In the first order transition, this is continuous for most of the part, but it becomes discontinuous and it could be a jump or a nick at the criticality.
At the critical temperature, yeah. So criticality is always refers to the critical temperature at which a phase transition is happening.
Yeah, for example, in the second picture, we have most area become continuous, but they have a jump then at the critical temperature.
Yeah. Exactly. Yeah. Okay. And so, are there more questions? Okay. And so, as it turns out, while we're so obsessed about looking at these diagrams, is that it turns out that you can have very different systems that all behave the same in the way of how they diverge at criticality. So you can all of a sudden put in magnets and fluids in the same box, which I mean crazy, like why would you do that? But apparently the physics of what's happening at the phase transition, the dynamics of how they do this transition is only governed by the symmetries of your system and all the microscopic details of how the entities that you have, the spins or your fluid particles are interacting. All that is pulled into the value of your critical temperature. So the critical temperature, like what the the temperature itself, the value of the temperature, that's still defined by the microscopic details of your system, but the dynamics of how it diverges, that's universal, therefore universality. That's a universal property that's only governed by the symmetries of the system. Again, we will all derive that, no worries. This is just like to happen. And so what we actually care about is to then describe these dynamics. I mean, dynamics not in resolved over time, but like how as I approach the critical point as changing the temperature of my system, of how this is governed. And so how this is governed, this is what we describe with critical exponents. And so what they do is they measure the form of the divergence of the specific heat and the susceptibility at the critical point. And so what as I said, like all the microscopic properties of our systems will fall into the value of the critical temperature. And so we will therefore only look at temperature relative to this critical temperature. So we've defined small t as temperature versus this critical temperature, again, normalized by the critical temperature. So we're only interested really in the deviation from the critical temperature. Why? Because this allows me now to really compare different systems in their dynamics, because we can now look at, how as a function of t, my susceptibility diverges. So, and then in general, lambda is it's called a critical exponent of a function f. F of this small t, in a sense that f of t scales with t to the power of lambda at criticality. So as we really approach this critical temperature, so for t small t small. And so when I wrote this down, I already made a big assumption, which will take us until Christmas to actually say that this is a good assumption. We'll prove this eventually. But, actually, the physical physicists survived for like over 50 years with this assumption, only then proving that this was right. So what we do here is, what I did is I wrote down the absolute value of the t. What am I implying if I say that the critical behavior depends only on the absolute value of t? Yes.
With the kind of
exactly, and that's not obvious. Like that's not obvious statement to make, right? That it makes no difference if I approach the criticality from temperatures smaller than your critical temperatures or for temperatures higher. We're going to make this assumption, and you will eventually see that this is a good assumption to make. So at critical, so this is true only as asymptotic behavior approaching criticality, and this means we assume same dynamics as t goes to t critical plus minus. Okay, and so it turns out we're going to need renormalization group to prove this. Okay. And so here it comes, another list of a cheat sheet, which is the critical exponents we care about. So apparently there's a whole zoo. I'm just going to throw them all at you, but bit by bit, we're going to play with them. So for magnets, the things like you have to see them so that you can solve the problem sets and not stare at this and say, like, what the heck does she care about, better, right? Here's better. So yeah, so that's the scaling of the magnetization. Then we have the correlation lengths. So should I give, maybe I can give this. Then that would be t minus mu for the correlation. My mu's and gammas. Let me try. So that's it. Mu. Okay. What else? Specific heat. And this is what is the field, and last the fluctuations. What are d minus 2 plus. And the same we can do for fluids. You will see that they're mostly the same, except for that we don't look at magnetization, but the corresponding functions, that would be the density, right? Yep. Correlation, it's the same. There we go. Instead of the susceptibility, we have the thermal, it's called thermal. Thank you. Oh God, thermal compressibility. But it's also the second order derivative. This is how it all comes specific heat. We have two, except for that we keep the volume constant here. And that's the jump in density to 0. Oh, the the jump in pressure. And that's the same again. So this is the whole list. And so, as I said in words already, why do we care? These critical. And the answer is universality. So the critical exponents are universal depending only on a few fundamental parameters. And only the critical temperature depends sensitively on details on interatomic interactions. And so a nice example is actually so these are different gases. And looking at mapping out their the temperature normalized by the critical temperature and the density normalized by the critical density. And so if you just normalize of the phase transition, right? So this is like the point where these gases become liquids. And it turns out I can have very different gases to look at. But if I just rescale the dynamics in terms of their critical properties, then they behave all the same. And so I think this is a very nice way to visualize that all the microscopic properties of these different gases, they all only lump up in the critical temperature and the properties of the system at that define the critical density or the critical magnetism systems. And all the rest is actually given by them being a gas, independent of these gases actually having interactions. So this is not like, don't think that this is about like idealizing the system. We're not. We're actually taking it. This is real data. Like this is with the full interactions. Yes.
If you go to the critical exponents, so I know from a bit previous knowledge that the critical exponents, the powers, come often coupled with scaling functions. And how do we work with the scaling function? From my experience, the scaling function, you have your critical exponent, then coupled with your scaling function, and the scaling function is for me often so omnious black box.
Yeah, so the scaling function we'll discuss when we talk about randomization group. I have to sadly ask you to keep patient because I have that scheduled for, I believe it's the week before the Christmas break or 2 weeks before the Christmas. So it's, yeah, so far this is, we just look at the critical exponents of like, say we are able to calculate the free energy for a system, and I calculate the magnetization and I rescale and I look at the dynamics of this magnetization as I approach the critical temperature. What's the exponent of that's to the taking the power to the temperature? So really think of it, and you will do this. Like we will actually explicitly solve there's a few systems that we can explicitly solve, like the harmonic oscillator, which you've been looking at in a classical and a quantum mechanical world. Here there's the Ising model that we can actually solve, and we can like see these factors emerging before we have to dig into the wonderful and diverse toolbox that we learn in this class of different theoretical models to get to these exponents, and and understand also crucial assumptions about these exponents, like that the behavior is the same if I come from above or below critical temperatures. And so this is different gases. Okay, so you can say like, oh, okay, gases, but I mean, they're all gases, right? They pass. So I can have the same exponents also across systems, right? So, for example, I can look at the magnetization for a magnet, a specific one, I can measure it. And here I find the spatter to be 0.335, and here's some variance in the last factor. Now I can also look at CCl4 plus C7F16, which is a binary fluid mixture. And there, remember magnet and density were this, when if I look at, they had the same exponent. So if I look at the density of the liquid with the fluid phase, and this, sorry, there's a minus. And look at this. And then here the beta is 0.33. It's the same. And I mean, this is crazy, right? That the magnet and the fluid behave the same. And that's the motivation for hanging out with me with the Ising model, is that also if I look at the magnetization of an Ising model simulation, I find beta equal 0.327. And that's the reason why we hang out and study the Ising model for so long, because it doesn't matter. And like I can describe these very diverse systems that all belong to the universality class, the same universality class. And then here again, I'm using this D because I have to specify the dimension of this universality class, which is 3 dimensions. It doesn't matter. Right? I can learn about how these systems behave as they approach criticality, even if I just look at something as simple as an Ising model, because they belong to the same universality class. And so this is actually here on a simple, just to give details, cubic, body-centered it really also doesn't matter where I run it. So that's the same exponent that I get on a simple cubic, on a body-centered cubic, and also on a face-centered cubic lattice. So really, if I have a simple model, important factor though is the dimension, as we're going to see. So for the last bit, I'm going to take you on on one more derivation. Namely, it turns out if I go back to this whole list of critical exponents, I can already see that they are related to each other. And so, which is again, a very fundamental insight, because it tells me that these dynamics of how I approach criticality are coupled, and I can kind of choose, if I have a specific system, which property I can measure nicely, and that even can tell me something about the behavior of the specific heat, because I can nicely measure magnetizations, but specific heat is harder to measure. Maybe it's actually easier, whatever. But I can exchange things. And I want you to bear with me, because I actually chose to give you the full derivation, because I always get myself frustrated if someone throws an equation at me and says like, this is true. And I want to really, see how it comes step by step. But it turns out that's also a perfect refresher of maximal relations, Legendre transformation, and all that you happily practiced in statistical physics. So bear with me. So what I want to show you are exponent inequalities. And a short refresher. Okay, and so the goal is, just so that we don't lose that, to derive a relationship for critical exponents based on their thermodynamic relationships. And so there are actually a couple. I will only have you bear with one. Namely, the example that we're going to derive is the so-called Rush-Brook relationship, named after the person who first derived. So what we're going to do is we'll start with the free energy of a magnet. And we write down the total derivative. So we have df is equal minus m dh minus s dt. Okay. And so you might remember that we can do a Legendre transformation to write this as df plus mh, which then is minus s dt plus h dm. And then for both of these thermodynamic potentials, I can write down maximal relations from the symmetry of second derivatives. So that means in this case, if you write down the Maxwell relation for the free energy, we have dm dt at constant field h is equal ds dh at constant temperature. And for this Legendre transformed potential, we have ds dm constant temperature is equal to dh, there's a minus, sorry. Minus dh dt at constant magnetization. And it turns out that these Maxwell relations constrain the Jacobian of conjugates. So just to give you an example and also introduce you to my notation. So if I look at the Jacobian of the st versus the mt, that's a shorthand for the stm constant t, the sdt at constant m, dt dm constant t, dt. So this is just notation of how I express such a Jacobian. And if I then take a value at the determinant here, that's nothing else as times dt minus dt dm ds dt ds dt, was it m? Okay, but now obviously there's a way of how to simplify it. dt dt, that's obviously 1. And also here I'm taking the derivative of the temperature field, but I'm actually keeping the temperature constant. So that has to be 0 because the temperature is actually constant. So this is 0. So that actually is nothing else than the S dm at T. And so similarly, I can write, this is for this side here, right? Just draw this line. And so similarly, I can also derive for the right-hand side of this Maxwell relation up there, that this is dHm dt. And so now how do these Maxwell relations constrain the Jacobian? So from Maxwell, we can now make the statement that the ST is nothing else. The minus, pay attention, we're copying that down, dHm dt, right? This is just rewriting this expression, now having expressed this as this complicated Jacobian and this as this complicated Jacobian. But now I can play with this Jacobian because of the commutations I can do with them to rewrite this as, since these are the same, I can write this as and then the mt comes up, dtm, right? So this is just flipping these two. When I flip those two, that's then I get a minus sign. This is actually just 1. Okay. So I can derive that this is equal to 1. Okay. Now, this is the recap of playing with Maxwell, Jacobian, and Legendre transformation. And now we aim to express the Jacobian in terms of response functions. Okay. So we start with that one that we know is equal to 1. But now what I'm doing is I'm expressing this one as the factorization of really writing out this Jacobian, which is so right now we just spelled it out, and now what I'm going to do is I'm going to dig into the toolbox and reorganize all these 4 terms. So this term, for example, we're going to expand by ds dhm, copying down, and now I'm just going to multiply it by dh dt m dt dh m. I hope you convince yourself that what I entered here is nothing else but a perfect 1. But what it's helpful for is that now I can write, and so the important bit is also to keep track of all these indices because I have to keep the same property constant, right? So now the magic is that this I can now rewrite as ds dt m. And now you need your cheat sheet from last week. This is actually already a response function, right? This is the temperature derivative of the entropy. That's the second derivative. And so that's the specific heat over time. This is the definition, keeping the magnetization constant. But then I still have this term to take care of, and I'm actually going to rewrite this as minus dm dh at a constant temperature divided by d m dt at constant field. Okay, second term. This one is easier because I'm just going to invert it, and that gives you a 1 over d m dt. Just going to write it that way. Why? You can already see, because then I can deal with these two terms. Going to do the same magic of multiplying with a factor 1 for this term. So again, copying down. dm dt. And then, so that's again, that's 1. But then this becomes ds dt now at constant field. And then this is again a specific heat, right? And wait, oops. And this becomes minus dm dh t over dm dt h. And that will make dm dt over h. And so reordering all this clutter here. Now we have that this 1 on the right hand side is nothing else than if I just collect cm over t. And then we have left there's a minus. Let me just put down the minus. dm dh over t divided by dm dt h squared plus ch over t. And here we also have dm dh t. That's this one here. And then divided, and again we have dm dt h squared. So by doing the appropriate reorganizations, we managed to arrive in a writing where all of a sudden we only have here a difference of the two specific heats, and they have exactly the same prefactor. So if I write it even shorter, and also actually identify one more response function, namely what we have here is the derivative of the magnetization with respect to the field, right? Remember the magnetization? That was already the first order derivative with respect to the field, first order derivative. And so here we also have a second order derivative that we had at the very beginning of today's class, namely the susceptibility. So this is nothing else than susceptibility. So taken together, we have then ch minus c magnet equal t dm dt squared. Now I will make the statement that the the specific heat at constant magnetization is some it's a positive value. So because then I can reorganize this equation as saying that this has to be bigger or larger, because this is I'm dropping this positive term T dm dt. Okay, and so now we're going to work with this relation that we derived only using thermodynamics. Big scale, I agree. And now what we're going to do is we're going to look at this and actually plug in all the all the scalings at criticality that we listed before. Question.
Excuse me, Professor. I was wondering if the sign should change for the minus CM.
If it's this which sign? Sorry, this sign or this sign?
Yes, that.
Let me check. So we have x ch minus cm. So this should be exactly that one.
Yes, but it went to the other side.
It went to the other side. Why did it go to the other side? I don't see it. Is there any, so this, what went to the other side is this factor. So this went in here, that's this one. And the t went there. But here, this x, ch minus cm. I don't see it. Do you see? Okay, so we're good. Yeah. Oh, okay. And so I won't scroll back, but now what we're going to do is we're going to remind each other that this was meant to scale with t minus alpha. This is deductibility. I mean, this is just nomenclature, which Greek letters you love to name all these. And dm dt is t beta minus 1. And so from the definitions. And so if we now insert this up there, then we can read that what we just stated is that t minus gamma times t minus alpha is bigger than, and the t I'm going to rescale as t minus tc over tc, so that's another t, and t 2 beta minus 2, right? It's squared, and so that's actually then equal t 2 beta minus 1. And what we did here when I rescaled the temperature is that we ignore all finite coefficients near the critical point. So like this. So if you put then all of this together, we can reorganize everything as a function on top of t, which is then minus alpha, actually write that, plus gamma plus 2 beta minus 2 is bigger than 1. So this has to be bigger than 1 for this statement above to be true as t goes to 0, right? T is measuring how we approach criticality. Remember, t was t minus tc over tc. So as I'm approaching criticality, small t goes to 0. And for this to be true, that this value is bigger than 1, this has to be bigger than 0, which says that minus alpha, alpha plus gamma plus 2 beta has to be greater or bigger than 0. And this is the Rush-Rook inequality.
Shouldn't we have -1 and -2 in the exponent?
-1, -2.
In the like in the exponent in the inequality, the last number is only 1.
The 2. Let me backtrack. And this is -2. Minus beta -2. Yeah, I see your point. I'm just trying to let's check below the Yeomans again. Sadly, Yeomans only gives did I close it? It only gives the inequality, but it doesn't derive it. Okay, there we go. The question was why it's a 2. Huh?
Was the exponent that was supposed to be
Yeah,
given then?
but
Yeah,
the
then-
exponent is I think the exponent will be with the 1 and not with the 2.
But it's weird, but
Could we go back to the derivation?
Yeah, just a quick question. Does anyone happen to have a MacBook who has a charger on them? I forgot to bring my charger, which I know is stupid, but I typically leave it at home. It would rescue the next 5 minutes for me. I'm sorry. We're, working on this. No one using MacBooks. Okay. So yeah, it's fine. Like hopefully we'll sleep soon unless anything. So Zoom apparently, like, it was fully charged when I started the class. So I hope I was hoping I would be fine, but apparently I'm not. So let's do it this way. Like, we keep discussing. I'm just gonna stop the recording just to make sure that I don't lose the recording, because that would be very sad, since at least the wireless did make us okay. Next time better. Sorry for those watching recordings.